Usually we use a very complex structure, try to define the complex relationship between x and y. So we will design several layers and stack them together. So it is called stack or called sequence. The layer we introduced right here, okay, it's a very simple one. Okay, we have activation function, we have some summation of different weights and input value. Okay, there are several different layers, different kind of layers which you can use in a neural network. So let's go back to right here. In this topic, okay, we just simply click this one. We have a sequence stack. And the website I provide right here is the library documentation. We only need to design what is the network structure you would like to use. When we try to write a program to implement your network, neural network, we use a library which is very useful, which is TensorFlow. TensorFlow has a package called Keras. It is officially supported by TensorFlow, okay, which is invented by Google. From my perspective, if it is possible, try to use TensorFlow and Keras because they're officially supported by Google. Okay, so there is a class called sequential. That means there are several different layers. You have to design your neural network. Right here, we can see that tf.keras.sequential means I would like to create a stack, or I would like to create a sequential. I need to define how many layers I would like to use, and in each layer, how many neurons I would like to use. So right here, you say Keras sequential, layers none. So here, maybe we can see there is an example right here. So you define a model TF Keras sequential, and it's an empty model. And then the second one, model.add, which means you want to add one layer to your neural network. And the first layer you add is a TensorFlow Keras layer, which is dense, D-E-N-S-E. Dense layer is exactly the same as what I draw right here. This layer has several neurons, and they receive information from the previous layer, and they have weight. And that kind of structure in Keras, that is dense, D-E-N-S. For a dense layer, it has 8 neurons. So the definition is 8. The input shape, which means information received from the previous layer, 16. The last line, model add TF Keras layer dense 4. That means I would like to add another layer to this existing model. So this model has 2 layers, and both of them are dense layer. One of them has 8 neurons, the other one has 4 neurons. So next question is, how many different layers? How many different kind of layers that Keras support? I strongly recommend you go to the website right here and click this one, model. Okay, here are some examples. Model equals Keras sequential. It has 3 hidden layers. All of them are dense layers. So 2 neurons, 3 neurons, 4 neurons. And we can define what kind of activation function we'd like to use for this specific layer. For example, it uses ReLU at the first and the second hidden layer. For the last one, okay, it has 4 neurons, but we don't apply any activation function on it. Okay, of course, you can name each layer. For example, layer 1, layer 2, and layer 3. TensorFlow Keras has layers, this big class. At left hand side, there is a category called layers. Okay, and you can see there are a lot of different layers right here. The dense, so you take a look at the left hand side, there are a lot of different layers. For example, convolution layers, LSTM, something like that. We'll talk about later. So make sure you understand all those things. The next layer I would like to talk about is softmax. This kind of structure is used quite often, so that I have to introduce it right now. A complex neural network may be this one. Sometimes we have multiple outputs. As you can see, in the previous model, we have only one y value, right? But sometimes, for some applications, you can have more than one target value. So these two different target values, they try to describe different relation between x to y1 and x to y2. And usually, when we design our neural network, y1, you can say that y1 means the probability of success. Sometimes for some applications, not all applications, I mean for some situation. Y1 means the probability of success, and Y2 means the probability fail. Right? Sometimes we need two values, and one is success probability, the other is fail probability. Okay. Of course, you can simply just use one value, for example, Y, to describe the successful probability. But usually, okay, we use two values to describe something. And of course, you can have a lot of different hidden layers right here and different hidden nodes. So when we do such kind of design, so here we have a lot of different ways, right? But at the end, as we know, the sum of the probability should be 1, right? So after you collect all the information right here, so we can see that the last layer of your hidden layers, H1, H2, and H3, those 3 neurons, they possess all the necessary information for the next layer to make a decision is success or failure, right? So make sure you understand this part. Usually, the last layer of your hidden layers, they provide, for example, three different points of views from all the previous information, and they have to make a decision right here. So we have something that way. They have to make a decision collaboratively to make a decision. Okay, it is successful or valid to decide the probability of successfulness or failure, right? So usually this is quite important because it has all the information needed to make such a decision. Of course, there are different weights right here. This weight will be the weight. Okay, the weight to calculate Y1 and Y. But there is a constraint that the sum of the probability should be 1, right? So we will use a softmax right here. Softmax right here. The softmax will guarantee the output of the value, the sum of the output value should be 1. That is quite easy. For example, for original Y1 should be like 5 and the other is 3. It's quite simple because after softmax, that is A 3 over 8. This layer is quite simple. Let's just try to squeeze all the values to a fraction, and the sum of them are 1. This is quite useful because sometimes we have a lot of application try to do probability regression. And usually when we do classification, that is the probability of class benign. Okay, that is the probability of class malicious. As we mentioned before, you collect a lot of network traffic or network packet. You use the field, header field, or any other information as the x1, x2, sn as the features, and you don't know how to relate x and y. That's okay, and you create a neural network, many layers and many neurons that pass the information from the left-hand side to the right-hand side. At the end, you apply a softmax onto target. One is class of benign, the other is so. After it's very easy for any others to understand your neural network. You have application, you feed in your flow data, net flow data, and your model come up a value. How possible this flow is malicious? So that is softmax. We use it quite often, so make sure you understand it. We have dense, right? We have dense layer, we have softmax. Okay. Next one. Take a look at the loss function first. Loss function. Keras has a lot of loss functions right here. Okay, we have talked about some loss function before when we talk about regression and classification. One of them is MSE, right? Mean square error class called mean square error. When I train my model, the loss function I'd like to use is MSE or any other one. Okay, there are a lot of different loss functions. For example, cross entropy right here, categorical cross entropy, binary cross entropy. That means I would like to do a classification model. Of course, there are some other loss function we don't even introduce right now because it is a little bit too complex. But right here, go back to here. When you design your model, okay, for example, let's say N3. N3 is good enough, okay, and its output value is y hat. So we use the training data from 1 to n and try to figure out what kind of parameter, which is W1, W2, and B, that can make this happen. We have minimum, right? Mean square error, right? We need to use this training data to help us to find out what is the weight, W1 to Wn and B, that can make this specific function, which is loss function, which is MSE, to be minimized. So that is a little bit complex. The y hat means after activation function, we have a lot of different weights minus y squared. And usually, as we mentioned before, we can draw this specific loss function in a space. It has the lowest point. Usually, we don't like to solve this equation. A little bit difficult to solve such kind of equation. So the strategy we take is that at the first place, we randomly choose weight. But it is square, right? Curved line. It has lowest point. And we don't want to solve where is the lowest point. So we randomly select the weight and we do partial differentiation. We know where is the direction to the lowest point. So we partial differentiation and we get to the direction. And move to weight. So the first round, we randomly select one weight and do partial differentiation. We know where is the direction of the lowest point of this loss function, and we move to the next point, and so on and so forth. So eventually, we can find where is the lowest point of the loss function, and we know what is exactly the weight is. So right here, in the neural network, the model, okay, the definition of the model is quite complex. But however, we can do partial differentiation on x1, x2, x3, so on and so forth, so that we can know the direction of w1, w2, w3, and move to the next w1 prime, w2 prime, w3 prime. And w1 prime, 2 prime, 3 prime, they can have a lower value of loss. 我们先选择一个随机的 weight， 然后去做 x1 到 xn 的偏微分，我们就知道 w1 到 wn 的方向。那方向往下走一步之后呢，我们就会得到更低的 loss function 的 value。好，因为那个 MSE 它是有平方的啊，所以在空间里面它一定会有最低。好，往下走一步之后呢，就继续走，走到最低点，就是 loss function 你可以走到的大概最低点为止的时候，那时候的 W 就是最佳的 W， 会使得你把所有的 training data 塞进去之后，对吧？有 n 个 training data 嘛 ，n 个 training 塞进去之后，整个 loss function 的和嘛，应该说平均的啊，因为刚好除以 n， 整个 loss function 的那个 MSE 啊，会是最低值。那我们就觉得这个 W 这一套 W 很不错，它可以描述 x 跟 y 之间的关系，使得 y 跟 y hat 就 y 的预估值，它们之间的平方差了哈，差平方和会是最小。那我们认为这是最近啊。那当然你可以选择我不要 minimize 这个 MSE， 就是我们认为我之前已经讲过了哈，在 regression 的时候，我们认为最佳这件事情其实是人为定位的。为什么最佳就一定要是 y 跟 y hat 相减平方最小叫做最佳？我可不可以3次方最小的？我可以8次方最小的最佳？我可不可以绝对值最小的？可以。我再讲一遍哈 ，loss function 的选定是人为，它并没有说那个一定是最好，好，只是我们很习惯使用在 regression 的时候使用 MSE， 然后在 classification 的时候使用 cross-M 去比较什么叫做最佳。那所以这个 weight 是在我们有一个前提假设，就是我们认为最佳是 MSE 的情况之下去算出的那个。好，这是人为的选择，但千万记得哈，这个不是一定的，这是人为的选择。Okay, as I mentioned before in our regression class, you choose one of the loss function, okay, which right here is MSE. But basically, you don't have to choose MSE. You can define your loss function by yourself. For example, I can do MSE, that is square, right? You can say I would like to do power 3, power 4, power 5, power 8 to define my loss function. So when you find your optimized weight, that weight you find out only fit the loss function you use. If you choose another loss function, the weight will be different. You can choose a lot of different loss function. So here we have different loss functions. If the problem is regression problem, we use MSE because it looks good enough. If it is a classification problem, we see if it is a binary classification. Then we use binary cross entropy, or we use categorical cross entropy. You can click those links. Okay, it will tell you what is the definition of how to use those loss function. Okay, so right here. So when you create your model, you should define what kind of loss function you like to use. So that is a loss function. So you have to define sequence stack, right? When you define your model, how many layers you want to use, how many neurons in each layer, and then you have to decide in each layer what kind of activation function you like to use to simulate the nonlinear relationship between the previous layer and the next layer. And you have to design the loss function, which means how do you evaluate your y and y hat? What kind of value you like to minimize? And usually we use MSE on regression problem, and we use binary cross entropy or categorical cross entropy on classification problem. The next one is optimizer. As we mentioned before, okay, we have to calculate all those weights, W, right? Now, how do we calculate those weights? Okay, as I mentioned, we do partial differentiation, right? To x1, x2, xn, so on and so forth, right? But after we know the direction of next weight, for example, from weight 1 to weight 1 prime. Weight 1 prime is the next. When we move our W1 to W1 prime, there are several different strategies that can help you to find the optimized W1 more quickly. Because we have a lot of data, right? We have n data, and we have to do partial differentiation many times, and it costs a lot of time to do such kind of partial differentiation and to calculate all those weights. So there are several different strategies we call optimizer. So here, in this example, we can see that this example, we have the second line, the TensorFlow Keras optimizer, SGD. SGD stands for gradient descent, okay? Gradient descent. And there's always a parameter called learning rate. Here is 0.1. So OPT is the object, right? And it's from SGD class. How do we run it? After you build up your model, okay, you have your sequence stack. OPT.minimize. In this example, the programmer define its own loss function. LOSS equals lambda 3 blah 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 blah. The programmer does not use MSE or any other predefined loss function. Okay? Define its own loss function. So when we minimize this loss function, okay, OPT.minimize loss. So when we say OPT operation run, that run means okay, start to do the partial differentiation, trying to find the optimized weight W. But what strategy we can choose? So basically, you can take a look at this one. Okay, we have a block, but I think it is good enough for you to understand different kind of optimizer, different strategy to quickly find W. Usually, finding those optimized weight for different strategy, maybe they come up same value of weight, but maybe one of the strategy takes 10 seconds to find the optimized weight, but the other strategy may take 10 minutes to find optimized weight. So finding those weights is not a problem. Okay, the problem is it takes too long to find those weights. So we select different strategy, different optimizer help us to quickly find a weight. When you go home, please take a look at this one. Okay, we have several different optimizers, but basically, okay, as I showed right here, they are partial differentiation. So theta, okay, theta is the next weight. How do we modify this weight? You do at the right hand side, you do the partial differentiation J theta. Delta means partial, the difference between partial differentiation and this current value. There's a weight called eta right here. That means I know the direction, right? Currently I know the direction because at the right hand side I do partial differentiation. But I say how big or how small I should forward to my next weight. 中文是这样说的哈，基本上所有的 optimizer 其实我们不太用管它哈，因为optimizer 的目的就是帮我们找出最佳的 W 嘛。那通常不同的策略找出的最佳 W 大致上会是差不多一样的，那当然也会有不一样的情况哈，但是通常比较特别。那找出那些 W 的时候呢，的缺陷是有一些策略可能只要10秒钟就可以找到最佳 W， 可是有些策略可能要花10分钟才能找到最佳 W。那因为我们的目的是找到 W 嘛就好，可是如果时间是我们的抗胜，因为我们不想等那么久，所以我们就会选择不同的策略。那这些策略大部分都像现在眼睛上看到这个样子，都是偏微分的。所以 J 后面那个 J theta 就是那个偏微分的差，偏微分的差啊。所以我现在知道那个应该是偏微分的方向啊，偏微分的方向。所以我现在知道偏微分的方向之后啊，我要从它这字写的不好，应该是 theta prime 等于 theta 减掉后面那个 theta prime 就是下一个 weight 的 下一个 weight 值应该等于现在的 weight 的值，然后往偏微分的那个方向去，所以是减掉一个偏微分方向。可是那个方向到底要走多远呢？那个伊塔就是一个参数值，那个参数值指的是我往那个偏微分的方向要走跨多大一步啊，然后才会得到下一个 theta prime。那这个走多大一步就很有值得聊的地方啊。我们刚刚不是看了吗？那个SGD 的那个方程里面有个 parameter 嘛，叫 learning rate 嘛，这个伊塔就是那个 learning rate。0.1 的时候就是我朝那个偏微分的方向走 0.1， 就是 x， 如果是 x1 的话，就是走 x1 走一个单位那边这个长度啊，然后使得我的新的 theta 就是 w1 等于旧的值减掉这个 0.1 乘以那个方向，就会得到新的 w1。这是最基本的，就是所谓的 gradient descent。其他后面所有的方式全部都是它的延伸啊，其他方式延伸。那你们可以去看一下这篇文章的内容，好吗？好，那我要讲的是，在选择不同的 optimizer 的时候呢，有一些想法。So basically, all the optimizers, okay, adapt from the gradient descent. So we have a direction of the partial differentiation. We have a learning rate, which is eta. So we take one step toward to the next optimizer weight. But what is the difference between different optimizers? Okay, one of the important concepts is called momentum. So for example, if we do partial differentiation, these two figures means at the very first beginning, we randomly choose rate. Basically, it should be, for example, weight 1, okay? That is weight 2, okay? This line means MSE, for example, equals 凹下去了，所以是5. That means MSE 4, MSE 3, MSE 2。中文来说，它就是像就是它有一个隐形的 z 轴啦，哈，它就是像等高线一样。那因为我们刚刚讲 MSE 就是平方嘛，所以这个圈圈就是一个等高线，可是它不是一座山，它是一座谷，可以吗？然后它有一个隐形的 z 轴哈，所以你现在看到的是等高线。那因为 MSE 应该是凹的哈，所以它往下走。At the very first place, okay, we randomly choose your W, right? W1, T, W2, T. At the very first beginning, you randomly choose at W1 and W2 at this red point. At the next run, when you do partial differentiation, so next run is blue color. If you want to have smaller MSE on the W1 direction, you should go right hand side, right? If you want to get a lower MSE value on the W2 direction, you should go this side. There are two partial differentiation. Combine them, they will go this direction, right? But we do it separately. 就是你现在在红色这个点嘛，对不对？你做了一次偏微分之后 ，W1 那个方向跟你说要往大的那边走，然后 W2 那边也跟你说这个 W 值要往大的那边走，这样子你的 MSE 的值才会降低。那虽然我们眼睛看是合力的向量就是往右上角，但是我是分开做的就是 W 那边做。So at the next data point is right here. Its value is W1, but however, that is the next t equals 1. That means after one round of partial differentiation. So you move to this point, but how far away you should move? Okay, we know the direction, right? We can calculate by partial differentiation. But how long we should move, it depends on eta, which is the learning rate. Okay, so if you have a larger learning rate, basically you can move faster toward the lowest point of your MSE. 中文讲没有？如果你有比较大的这个eta，或者说你有比较大的这个 learning rate 的话，基本上你在走的时候，每一轮在走的时候，你可以走得比较远嘛，对不对？因为方向是固定的嘛，但你会走得比较远。However, if you have a larger learning rate, maybe you will go for the next round. You will go to this point, larger E, right? So maybe you go too far away. Sometimes it's really depend on the shape of your MSE value. 就是你可能会你eta 是很大，你会觉得走得比较快，对不对？可是你看在这个例子上来说，你eta 是很大的话，你往那个合力的方向去，其实你已经走得太远。 对吧？这个是很直观的事情。你走太远，你就没有到达那个盆地的最下面。所以 learning rate 设大跟设小，其实是一个两难，它是你设计的时候要考的事情，而且很多时候是我们根本就不知道，所以我们都是跑了实验才知道。比如说你怎么一直找不到低点就是你走好多 round 之后，你怎么觉得 MSE 都没有下降？然后 MSE 下降就表示你在这个谷地里面绕不出去，或是绕不到低点嘛，对不对？绕不到低点，或许就是说你 learning rate 就是小一点，而且 learning rate 设很小的话，你就在那个山坡上慢慢的往下爬，有时候要爬很久才爬到底，这都是有可能。或者是说，因为那个公式很复杂嘛，所以不可能只是一个这么单纯的像盆地那样的，它其实是一个起伏的山跟盆地交错一个超级奇怪的这个多维的空间的一个坡这个坡你要走吗？你可能有2-3个谷地，可是其中某一个谷地才是最低。那有时候你会卡在谷地里面嘛，对不对？那你要卡在谷地里面，你要怎么离开那个比较浅的谷地，跑到深的谷地里面去找最低点的？那可能learning rate要设大。所以这个都非常非常不一定，这个都非常看你的资料跟你的那个loss function 的那个最后的形状长什么样子这个是没有一定的。所以 learning rate 是一个很难的题目。就我们目前的角度来说呢，我们就是设一个常见的 learning rate， 就好像是1/1000或是1/1000，然后就让它去跑跑10分钟，跑20分钟不管了，反正就是跑。所以我觉得这件事情就是目前还没有比较有定论的方向，好吗？这是 learning rate。OK， When you design your model, okay, you may have a very strange MSE surface, and you want to find the lowest MSE value point. Maybe there are 2 bases, and one is shallow, one is deeper. But if your learning rate is so small, so that you cannot get out of the shallow basin to the deeper basin, then you may never find the lowest MSE value. So sometimes setting learning rate is art. Usually we don't know how to set this learning rate. Again, basically the recommendation value of the learning rate is maybe 1/1000. Let's go back to the blue point, okay? However, for the first round and for the second round, for the third round, for 4, 5, 6, we can approach to the lowest data point, okay? For example, at the last, this one, that is the last point we found. So right here, we can find, okay, that is the W1, the optimized one. And then here, this one, that is the optimized 2 star. So that is the weight we use in our model. It takes a long time. For example, 1, 2, 3, 4, 5, 6, 7, 8. Okay, it takes 8 different W to find the W star, optimized W, right? So, however, you take a look at the other figure right here. For example, W1, and we have a random choose W1. Okay, momentum means when we go this way, that is the first direction we would like to go, right? And the second direction is right here. So the first direction is right here, and the second direction is right here. For the first direction and the second direction, maybe we can create another concept called momentum, D1 and D2, okay? D1. And the second direction of partial definition is D2. And we can see that there is a combination direction is right here, and it has a direction, and we call it momentum. Momentum 的中文要怎么翻？动量，就是说，你看我们第一步要往右上走，然后我们第二步微分跟我讲要往右下走，是不是好像都是要往右走？所以如果我在第二次的时候第二次之后，我们不是要改变我们的方向跟跨步吗？对不对？我可不可以多的就多一点点往右走的这个感觉？也就是说呢，我的 W 本来应该是 W 减掉一个learning rate， 然后这个微分的方向嘛，对不对？我再乘上一个东西，让它往右多走那么一点点，那我是不是感觉起来会走得比较快？这个就是 momentum。但它的数学形式不是我画这样，我画的比较简单，然后数学形式不是这样子，就是说我在每一次走的过程当中，我把过去走的方向也稍微的考虑一下。如果我一直往正确的方向走，那就是 W1 一直是往右走的话，那我每一次就走得越来越快，越来越快，越来越快，都一直往右走。这样子我在往右走，搜寻到 W 新1的过程当中，会快一点点， 其实没什么特别的，这件事情跟 neural network 基本上没有关系，它只是在微分走最低点的过程当中，可以挤轮数比较少，可以走得比较快。它会不会还是找到那个 W 星呢？大致上来说还是会，只是快跟慢的差别。Okay, so the momentum means that for the first time, okay, I know the direction is D1, and for the second time, after partial differentiation, I know the direction is D2. And we can see that the combination of these two different directions, it has a combination toward right, and we call it momentum. So when you update your weight, we can consider that we can add more momentum to the right hand side. So for example, for W1, originally it can move to next W1, right, by using W minus eta. Eta is the running rate times the direction of right. But the momentum, so I can move even more bigger than the original gradient descent. So that I can move faster because of the momentum. So I can have less run to find the optimal.